Good evening, dear student, and welcome to this other edition of our functional analysis class. As I promised yesterday, we will continue. We'll proceed with examples of how to show that an operator is bounded, a linear operator is bounded. Okay, so where we stopped yesterday was at this level where we are supposed to apply Holger inequality, or from here, use the fact that, okay, so that's another possibility. So I'll call this star. Right? Okay, from start, we know that this gy is less than or equal to, because it's in L infinity, it's less than or equal to the supremum for all y, because y here is taken throughout the R, yeah, for each y, right? So for each y, it is less than the supremum of this. Of course, we take y in. Instead of R, I can even put x, but x in R, because it's a dummy variable. Right? Even put x here, x in R. And this supremum is the infinity norm, or the L infinity. You can put infinity or L infinity, it's the same thing. So now, so this entire integral will be less than the integral of f of whatever is there into the supremum, that's the norm. So I will just write it here. I'll say star implies the absolute value, the absolute value of f g of x, like this, right? Because that is our, yeah, this one. So our, this is less than this, which in turn is less. So I'll write the second less directly. So I will say this is less than or equal to this integral absolute value f of minus y, and then we have this dy. So I take the upper bound of this, where I substitute this with that one. But you see that this does not depend on y. I can take it out the limit of integration, right? So I consider that this is equal because I'm taking this outside. Integral dy, because so this is a function of x. This depends on x, right? So that is what we have at this level. Now, I could have used the other definition. In fact, the other one would be even easier. Or even from here, I can still use a change of variable here. But the best thing to do at this level is to use is to use this, because I said that these two are equal. So I can use this one instead. This one. So in order to avoid the usage of the change of variable when it is f of x minus 1, I can use this integral instead. Then I will take the supremum for all the of everything here. That is x minus y, since they are in R. Y is in R. Well, if I add any x, is still in R. So all this might be my new variable, and then I take that once instead of using the change of variable here again. And it's a bit more complicated. So what is it? What I could have done here, I could have used the definition where this is G and this is F. Right. So let me modify that. That is to simplify. To simplify the computations. So here I can use G. Okay, so I can say that this is f of y or g x minus y f y d y, and then I erase this part. Okay, so we still have our alpha. So this is Fy absolute value. And now this I can review. But now what I can do here, is to write x minus 1. Right. Okay, so all this is still less than that. Then I come here, I'll write this x of f of y and then inside I will not need to perform a change of variable here anymore. Good. So now this is where we are. And what is f? We say we take f where? F is in capital X, and what is capital X? Okay, capital X is L1. So the norm. So this is the norm already, so that's the norm. So this is the norm, right? This gives us the one norm. So this, like this, is the L1 norm. So I can say that this is less than this norm times that norm, which I can rewrite here. So less than or equal to the L1 norm f into the L infinity norm of G. So you see that this is true for any x. And here I don't have any x. You can see from here that x is not. So I can take the supremum or the essential supremum. What exactly do we want to? Because everything will depend on what we want to achieve. Okay, so this one we want to show that f is in what? y, which is the L infinity. Okay, so then we take the essential supremum, which would be the L infinity norm. So that's what we will do here, because we're in that space, right? So since this is true for any x, right? Or if you want to say for x in R, that is, if this inequality is true except for a number of x, that in fact for x in a negligible set, that is, except for x in a set whose measure is 0. Right, that's the essential. So from here, we can just say that this implies we then take the essential supremum So what does this imply? We have two results at the same time. We have this result, right? That's what this means. That what is here inside belongs to L infinity. Why? Because this is finite, right? It's finite. So I can already say that this implies that F convolution G is in L infinity, right? But at the same time, we have the bounded operation. In fact, we have the fact that our operator is bounded. What is the definition of our capital F of F? It's known. What is it? Capital F of F is this one. Now, it means that its essential norm is less than that. So we can write here. So it also means at the same time that this norm, which is in fact the norm of this, the convolution, right? I can write L infinity or infinity there, but let's put L infinity is less than or equal to the norm of G, that is infinity norm. Of course, I can change the position, doesn't matter, right? Into, because what we want is the norm of F. The L1 norm of F. That is, this is like a constant multiplied by the norm of F. Now, this constant K is this. This is our K, which is positive. It is strictly positive because our G, we saw that G is strictly positive. Right. So in other words, you can see this is capital F applied to a function F, and its norm is less than or equal to a certain constant times the norm of that element or the argument, if you want. Because remember, we have T, we have the argument of T. This norm is less than or equal to a certain K, the norm of the argument. That is it. So our X here is like our lowercase f. And this is our operator capital F. We take the norm less than or equal to a constant times the norm of the argument. So that's what we have. So this implies that we have a bounded linear operator. And K is the norm, the infinity norm of G. And since G is positive, K is also positive. Cannot be 0. Okay, and at the same time, I can conclude, because we also define the operator norm. Let me conclude thus. F is bounded so it is bounded and its norm, because remember, when we have a bounded operator, you can say something about this exists, right? The norm of the operator. But now we know that this is always less than or equal to all these k's. Not all, but since this is the infimum of all this such k, is particularly less than one of the k's, which is our G. Because remember that the norm okay, so remember that the definition, if I want to write the definition of this, since, I can write here, since by definition the operator norm, that is the norm of F, is what? Is the infimum of alpha such that less than equal to alpha. So what does this mean? It means that if I have alpha that satisfies this, right, this norm is less than equal to that alpha. For such alpha. And in particularly, we know that for alpha equal to G, for alpha equal to the, so I will say that in particular, for alpha equal to this we have right. So this is the justification for I'm connecting this since I still new, so I have to sometime repeat so that you grasp. Okay, so yeah, that is it. So I hope that with this little explanation, or the in-depth explanation, not little, I say, you understand more and more. All right, so that is it. Okay, I will quickly do the next one, right? I wanted to skip this one, but I thought it should be better to do that extensively so that we can. So, okay, so that is example 1. Now for example 2, And example 2 is similar to example 2. The only difference is the spaces L and X and Y. Because in example, okay, so now here we take X equal to Y, and both are equal to the set of continuous function over the closed interval AB. Right. Okay, this is for 2. Now for 3, X and Y now, instead of being C, they will be equal to L2, right? L2, both, okay, but, and the number will differ, right? Because of the choice of X and Y. So I'll do only for this one, right? Okay, so that is this, but now we are going to define the operator. We're going to define the operator. Okay, so we are going to define the operator. So we define, first of all, the norm. Wait. The norm. So the norm that we are taking here, right, we need a norm space. So we know that we can define the infinity norm here, and that's what we are using. Yeah? Infinity norm equal to what? Take the infinity norm, right? Which is what? Which is the supremum. Okay, instead of doing that, I will put f here for any f there. So whatever I put here, I will take the infinity norm of that. If I put f here, f there, then I'll take the supremum of f, right? I just put a dot here to say it's a function. Okay. This is x, and then I take x in the closed interval AB. So that's just to say you take the infinity norm, right? Okay. So it's defined already. We have that. Now, our operator, we are going to use what we call the Fredholm operator. Fredholm operator. We define the Fredholm operator we define the Fredholm operator A, right, from X to Y. So at okay, we can take f there instead of x. We can use f. And then to a, we apply af. I can use a parenthesis or I can leave it like that, right, like this. A apply to f. As we did for capital F, we do the same thing. So we take, because this is a continuous function, we apply it to x in the interval AB. Right. So so we define this as or by A F A F at a particular point X is an integral. So a bit similar to the previous one, but a bit different. So we'll call this, okay, instead of taking x, we can use t. Yeah? I want to keep the notation. Okay, anyway, let us leave that. So this is y, okay, yx, y of x. Okay, or y of t. Okay, anyway, yx. So we call this yx, right? Like this. And this is an integral. So this is the integral from a to b of what? Of a certain kernel, k. Okay, but for the kernel, generally it is ts. So I will change all the x to t. So k, s, and this is what we call the kernel, k for kernel, of that of the operator a. So now this f, put it here, s ds. So you see that it's a bit, not completely. So it's a bit similar to the previous operator, this one. Where did I define that? Okay, here. You see that this f is applied at y, and then here in our kernel we call it ks ts, or I can say kxy. Right. So k, the kernel here, is like this, and you can see that g. If you look at it's true that it's a single, because this g is a function of a single variable. So you can see that you have x and y, both of them there. But if it's a function of two variables, then it's like our operator, as our kernel k of x, of ts. Right. It's a bit similar, but it's not exactly the same, because here you have the difference of the two variables. But just to tell you, it's a bit similar, right? It's not exactly the same thing, but it's a bit similar. Okay, so this is the definition of the freedom operator. So this is how we define it. Right. So this s is in an interval AB, and this t also, we take t also in the interval AB. Right. Okay, but this y in fact is AF, so it's a continuous function at a particular point, because it's here. So that t is also in AB, right? Okay, so k is what we call the kernel. I will not write it anyway. So A is linear. Linearity is exactly the same way. It's similar to what we did the other time. I will not do that here. I will just say A is linear. This is trivial. So trivial. So and similar to what we did above. I will not do that. I will not repeat that. And it's bounded. What does that mean? That we can find k or alpha, something positive, such that the infinity norm, because remember that we are using the infinity norm in x and y is less than or equal to k times the infinity norm, because we are using infinity norm, and this should be true for any f. For any f in CAB. Right, so that's what we want to prove. So this is what we want to prove. Now, if I start from here, so I fix t. So fix t, so that is an arbitrary, this is an arbitrary t in the interval AB. So I'm using this I'm using that this definition. Okay, let me even copy it directly. So I start with this one. So the absolute value of this, right, which is the same, is also equal to the absolute value of this, which is equal to this one. But this absolute value, the last one, is less than or equal to the integral from a to b of the absolute value. You can break that absolute value in two like this. K Ts Fs ds. You see that T is fixed. When I fix it, it's fixed. And I apply this, right? Okay, we know that F is taken where? F is taken here in X. And in X, we have the infinity norm. So this is less than the infinity norm of F. Right, so I can even write it here. Less than equal to infinity norm of F. So I can take it out because it doesn't depend on S. Take it out, right? I can take it out, of course. So this is equal. So I can write equal and I take it out, but I can write it with this one. So once I take that out, I want to say something about this operator before I conclude, right? So K is a continuous function. This is K, the kernel, right? The kernel K of A, right, is a continuous function. So we are using that, right? This is an extra information that I am supplying. It's a continuous function on the closed interval, which is compact, right? On the compact set of R2. That is the interval AB. That is for the first variable, t. Remember, we said t is taken in AB, right? Into the second one is s, and s is also in AB. So we know that this is compact in R, this is compact in R, and the product is compact in R2. So a continuous function on a compact set is bounded on that set. It attains its maximum and is bounded there. Right. So that's what so it is therefore bounded. It's therefore bounded. So if it's bounded, what does that mean? It means that we can find a positive m such that in absolute value, k ts like this is less than or equal to that capital M. That is true for any t and s, both in the closed interval AB. Okay. Now, if I take this into, I call this double star, right? So meaning that I can write that this imply, so this information imply using double star, this imply so we say double star implies, of course, using this information, the boundedness of the kernel, that A, F applied to T is less than or equal to the integral from A to B, capital M, right? Because I can put substitute of, I mean, less than or equal, then this one is there because it's less than or equal. And then we have the norm. In fact, these two are constant, so I can take them. So this is equal to, now if I take these two outside, this integral of dx will just be b minus a. So I can say b minus a m into, so now this is our k, lower k, and it's positive. M is positive, b minus a is positive because b is greater than a, right? And we are done. That is our k. But you see, this t is fixed, right? It's arbitrary. Now, if I take the supremum also, because remember that we are using the infinity norm. So this implies that the infinity norm AF, which is equal to the supremum of this, for t in the interval AB, right? This is less than, so I'm applying the supremum to this formula. So this is less than or equal to b minus a m into the infinity norm of f. So you see, this is what I indicated above here, that this is what we want to show. So you see that we have the infinite number of L, which is here. Whatever constant multiply it is our K, which is positive. Right. And this completes the proof. That's what we wanted to prove. So complete the proof. Okay, I think we will stop here. This gate is already late. Similarly, the next one is exactly the same operator, but now we change X and Y to be L2. You just make sure that you use the L2 norm, that's all. So, and it's even in the notes, so you can read that. Now that I explained all this, I hope you'll be able to understand that one. All right, thank you for your kind attention. God bless you and see you next time. Maybe tomorrow I will record another one. Okay, bye-bye. Enjoy this time. Please read the notes. Make sure that you cover everything on linear operators so that next time it will be easier.